Welcome. In this video, we're going to discuss the planet Jubilation. So you can picture landing on this planet at a random day in time and wanting to know what are your chances of having a good weather day. Now our weather for this planet is going to be in binary. It's just either good or bad. Now if it's good, it remains good 70% of the time, kind of like the planet Earth. If it's bad, then it remains bad 60% of the time for the next day. We're going to let A sub n be the probability that the weather is good on day n. So we'll think cup half full, our A sub n represents the probability of a good weather day. So our job is to find a recurrence relation and solve the recurrence relation, and then ask one further question. What happens if we landed on Jubilation on a random day? What are our chances of having good weather? So let's start out by writing down some of the probabilities that the question gives us. Let's represent G for good, and the good weather day could stay good, or it could transition to a bad weather day. On the other hand, we have the possibility that a bad weather day could transition to a good weather day, or the bad weather day could stay bad. Those are the only options we have. So the probability of the weather staying good is 70%. So let's write 0.7 for that. Now if it switches over to bad, that would happen at 30%. So we'll write everything out of one, write our percentages in decimal form. Now the bad weather days stay the same 60% of the time, and they swap over to good weather days 40% of the time. So we'll picture this top line, let's say as day n minus 1. So this is day n minus 1, and then we transition to day n. This is going to help us build our recurrence relation. So what this tells me is that A sub n, when it's representing the good weather day, the probability of having a good weather day, we can look back to the previous day, and we're saying that, okay, we know that A sub n minus 1 is the probability that the previous day was a good weather day. And we can say, okay, in 70% of that time, it remains good. Now, or the previous day was bad. So when I say or in probability, that's when I want to write a plus sign. The other possibility that can occur is the previous day was bad. So the chances of having a bad weather day on the previous day is 1 minus A sub n minus 1, the opposite probability. So it's saying that our weather is not good, or our weather is bad in terms of probability. So the probability that we swap over to being a good weather day would be 40%. So this is how we can build our recurrence relation. So once again, the first term represents the probability of a good weather day transitioning to a good weather day, and the other term represents the probability of a bad weather day transitioning to a good weather day. Those are all the possible ways that you can get a good weather day. Now, one issue here is this particular problem didn't give us any starting point. It didn't say, the chances of a good weather day on Friday is 50% or anything like that. So we don't really have an initial condition to start this sequence off. So the best that we can do here, there's no initial condition, is just make up one. We can just say that, okay, A sub 0, let's say, on the very first initial day that we start our counting from, it has a probability of P for being a good weather day. So this builds our recurrence relation. So we found the recurrence relation, and now we would like to solve the recurrence relation. Now maybe before we do that, maybe it would be nice to just simplify A sub n a little bit. So we notice that we can combine two terms with the A sub n minus 1s. So we would get 0.3 A sub n minus 1 plus 0.4. It's nice to have our recurrence relation in a kind of a simplest form. So this here is the recurrence relation. Now, one thing that we could do just out of interest's sake, the question does say, well, when n gets really, really big, what is a sub n? It does say, well, what happens when n goes to infinity? If you knew that this particular sequence converges to a particular probability, there's a little bit of a trick that you could do here. You could just say, well, at some point, a sub n will equal x, and it'll just stay as x, even if we go to the next term in the sequence. So you could say that a sub n minus 1 is also x. So this would be the point when it finally converges. So then from here you could say, okay, my x value is equal to 0.4 divided by 0.7. And that's approximately 57%. And this kind of makes sense. The weather was slightly favored towards the 70% versus the 60% for staying good versus staying bad. So you get about a 50% shot at your weather being good if you landed there on a random day. Now, of course, this assumes that our sequence of numbers does converge to a particular probability. And the question also asks us to solve the recurrence relation. So we haven't really done either of those things. So let's erase that and try to solve our recurrence relation. So using iteration, a sub 1, the previous term was p, so we get 0.3 p plus 0.4. Now our next term in our sequence, a sub 2, we take everything that we had previously, multiply by 0.3, so we get 0.3 to the power 2 p plus 0.4 multiplied by 0.3, and then the final thing that we do is add on a 0.4. And we keep doing this, remember not to simplify, until we notice some kind of pattern that occurs. So 0.3 gets multiplied by everything from above, so 0.3 cubed p plus 0.4 times 0.3 squared plus 0.4 times 0.3 and then plus 0.4. So hopefully at this point we're noticing a bit of a pattern. We get a geometric series with powers of 0.3. If you like, you can add on a 0.3 to the power 0 at the end here, and maybe we'll write 0.3 to the power 1. Now, in order to isolate that geometric series, let's factor out a 0.4. Or maybe let's just consider what happens once we go up to the nth stage first. So maybe dot, 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 a sub n. Eventually, at the nth step, we'll have multiplied by 0.3, enough to get the power of n, and then multiplied by p. And then we'll factor out all of the 0.4s. And then inside of a big set of brackets, we get a geometric series of 0.3. So 0.3 to the power n minus 1 plus 0.3 to the power n minus 2, dot, 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 all the way down to 0.3 to the power of 0. Okay, so we do have a solution to our recurrence relation. It's sitting right here. It's not really a very nice solution because you still have to deal with an open form. Whenever we can find closed form solutions to our recurrence relations, we certainly should, because the whole point is to get a nice formula that can calculate any term in your sequence quite quickly. And the open form, unfortunately, doesn't quite do that for us. So 0.3 to the power n, p, this term is kind of off on its own, and the rest of the terms are being multiplied by 0.4, and all of those rest of the terms are forming our geometric series, so we can go ahead and use that formula right now. We'd get 0.3 to the power of n minus 1 over top of 0.3 minus 1. So there's our solved form of our recurrence relation. Now, another thing that we could do at this point is consider what happens when n gets very, very big. So what happens when n goes to infinity? So as n goes to infinity, a sub n equals a certain value. Let's think about what that value might be. Well, as n gets very, very big, the 0.3s all just go to 0. So that one goes to 0. This whole term is 0. On the top here, we have minus 0.4. So we have minus 0.4, and then on the bottom, we have 0.3 minus 1, so minus 0.7. And this is the same result that we got earlier in the kind of quick method of approximately 57%. So that completes our problem. Thanks so much for listening, and we'll see you on the next one.